Imagine you've built the next big app. At first, it's just you and a few friends. One server handles everything perfectly. But then your app goes viral. Thousands, then millions of users start hitting your server at once. Suddenly, that single server is sweating. It's overwhelmed. The CPU is at 100%, and users are seeing those dreaded 504 gateway timeout errors. This is the single point of failure problem. If this one machine crashes, your entire business goes dark. We need a way to spread the work across multiple machines so that no single one is crushed under the weight of the crowd. This is where the magic of load balancing begins. It's not just about speed, it's about survival in the modern web ecosystem. Without a way to distribute this massive pressure, even the best software will eventually fail.
When your app grows, you have two choices. First, vertical scaling. This means buying a bigger, beefier server with more RAM and a faster CPU. But there's a ceiling to how big one machine can get, and it's expensive. The second choice is horizontal scaling. Instead of one giant machine, we add many smaller, cheaper servers. This is much more flexible, but it creates a new problem. How do we decide which user goes to which server? If a user types their URL, which IP address do they hit? We can't just give out 10 different IP addresses and hope for the best. We need a traffic cop, a conductor for our digital orchestra to sit in front of these servers and manage the flow of incoming requests efficiently. This traffic cop is the load balancer, and it's essential for horizontal scaling.
Enter the load balancer. Think of it as a high-speed receptionist for your data center. It sits between the public internet and your private back-end servers. When a request comes in, the load balancer receives it first. It looks at its list of available servers and says, you go to server A, and you go to server B. To the user, everything looks seamless. They only ever interact with the load balancer's IP address. Behind the scenes, the load balancer is doing the heavy lifting of routing packets. This architecture allows us to add or remove servers on the fly without the user ever knowing. It provides a single entry point, making the complex infrastructure behind it look like one unified, powerful system. It acts as the face of your application, shielding the complexity of your internal network.
So, how does the load balancer decide where to send the traffic? The simplest method is called round robin. It's exactly what it sounds like. The first request goes to server 1, the second to server 2, the third to server 3, and then it loops back to the start. It's fair, it's simple, and it works great if all your servers have the same power, and the requests take roughly the same amount of time to process. It's like a dealer at a card table giving one card to every player in a circle. However, round robin isn't always the smartest. What if server 2 is processing a very heavy database query, while server 1 is just serving a tiny image? Round robin would still send the next request to server 2, potentially making the bottleneck even worse. It's a blunt instrument for a delicate job.
To solve the limitations of round robin, we use smarter algorithms like least connections or IP hashing. Least connections keeps track of how many active requests each server is currently handling. It sends the new user to the server that is the least busy at that exact moment. This is much better for long-running tasks. Then there's IP hashing. This uses the user's IP address to calculate a unique key. This key always points to the same server. Why would we want this? For sticky sessions. If a user is mid-purchase and their shopping cart is stored in the local memory of server A, we want to make sure they stay on server A until they finish checking out. These algorithms ensure that traffic is not just distributed, but distributed intelligently based on real-world conditions.
One of the most critical jobs of a load balancer is performing health checks. It's constantly pinging your backend servers to ask, are you okay? Are you still breathing? If a server stops responding, maybe its hard drive failed or a software bug caused it to hang, the load balancer immediately marks it as unhealthy. It stops sending any new traffic to that broken server and reroutes everything to the healthy ones. The best part? The user never sees an error message. They might experience a tiny delay, but the service remains up. Once the broken server is fixed and starts passing health checks again, the load balancer gracefully adds it back into the rotation. This self-healing property is what makes modern websites so reliable, even when hardware fails.
Now, you might be thinking, wait, if the load balancer is the single entry point, isn't IT a single point of failure? You're absolutely right. If the load balancer dies, the whole site goes down, even if you have 100 healthy servers behind it. To solve this, we use high availability pairs. We run 2 load balancers, one active and one standby. They use a protocol like FreeRRP to share a virtual IP. The active one handles all the traffic, while the standby one watches it closely. If the active one stops sending a heartbeat, the standby one takes over the virtual IP in milliseconds. This redundancy ensures that your traffic cop has a backup cop ready to step in at a moment's notice, providing 99.99% uptime for your critical applications. Load balancers also handle SSL termination. Encrypting and decrypting HTTPS traffic is computationally expensive. If every individual backend server had to do this, they'd waste a lot of CPU power. Instead, we give the SSL certificates to the load balancer. It handles the handshake with the user, decrypts the request, and passes it to the backend servers over a secure private network. This offloading makes your backend servers faster. Additionally, load balancers act as a first line of defense against DDoS attacks. They can filter out malicious traffic, block suspicious IP addresses, and ensure that only legitimate requests reach your actual application code, keeping your data and your users safe from external threats.
In the old days, load balancers were massive, expensive hardware appliances sitting in a rack. Companies like F5 dominated this space. While hardware load balancers are incredibly fast, they are hard to scale and very pricey. Today, most of the world uses software load balancers like Nginx, HAProxy, or cloud-native solutions like AWS Elastic Load Balancing. These are much more flexible. You can spin them up in seconds, configure them with code, and they can automatically scale up or down based on how much traffic you're getting. Whether it's a small virtual machine running Nginx or a global-scale Google Cloud Load Balancer, the core principles remain the same: reliability, efficiency, and seamless distribution of work across your entire fleet.
To wrap up, a load balancer is the unsung hero of the internet. It provides horizontal scalability, ensures high availability through health checks, manages intelligent traffic distribution, and even boosts security and performance through SSL offloading. Without them, the massive websites we use every day, from Netflix to Amazon, would crumble under the first sign of a traffic spike. Next time you load a web page instantly, remember there's likely a load balancer working tirelessly behind the scenes to find the perfect server for you. Thanks for watching. If you found this helpful, don't forget to hit that like button and subscribe for more deep dives into the world of system design and architecture. See you in the next one.